Thank you for selecting the Beckwith Electric Video 2001D enhancements over the 2001C. I will be your host today, Bob McFetridge, and we'll be spending approximately 45 minutes describing some of the new features that are available on the D that were not available on the C. To start with, the C is completely compatible with the D and vice versa. So from a physical standpoint, the 2001D uses exactly the same adapter panels as the 2001C. This allows a customer that has a 2001, a 2001A, a 2001B, or a 2001C to replace it with a 2001D by simply removing the blue plug and the 4 screws off of the existing control and then placing the new control in the same adapter panel. So the blue pin connector on the D is pin-to-pin compatible with the C. With that in mind, we will then start talking about these basic topics. The first being user interface features. Then we'll talk a little bit about new communications features available. Then go to power quality. Then we'll talk specifically about features that are targeted for LTC applications. And we will finish up with features targeted specifically for regulator applications, as the 2001D can be used for both single-phase regulators and for LTCs. So, looking at the front of the D, we will notice a few things right off the bat. First of all, the C prior had a front port RS-232 port for configuration. That has been replaced with a USB slave port. This can be purchased, the cable for this can be purchased at any store, Walmart, Best Buy, and it's basically just a USB printer cable. We also have the advantage of having the baud rate be 115K, so the support will be a little faster. And finally, the older controls all used BECO 2200 as the internal protocol between TapTalk and the control. In the D, we are now using Modbus protocol between the TapTalk and the control. This does mean that there is a different version of TapTalk specifically for the D. So there will be two different versions of TapTalk, one for the 2001 A, B, and C, and then a new version that will be specifically for the 2001D. So we feel that we've upgraded the connection for the local operator via the laptop. Secondly, you'll notice that the HMI has changed. We now have more buttons, and some of these buttons have hot links which allow you to go directly to a certain area. With that, one of the buttons is programmable. This is what we call the wake button, and using the new TapTalk, it allows you to take any quantities from this side of the screen, drag them and drop them to this side, and then you can sequence them in any order you want. The purpose of this button is to allow operators who don't know the panel that well and interface with it infrequently when they're doing switching to have every piece of data they need mapped to one button. Then the operator simply places his hand on the button one time, and it'll scroll through the quantities on this side with about 2 seconds per screen, and it'll stay in a loop. If he hits the button a second time, it'll stop on whichever screen he's on, and then using the up and down arrows, you can navigate through at a slower pace. If you hit the button a third time, you will exit the wake screen and go back to the main menu. So the wake button is mainly for linemen. It allows you to customize what quantities they're going to see. Then in one button pressing, they can see those quantities in a loop, or pressing it a second time, they can use a scrolling manner, or a third time, and they can leave that window altogether, and then they can access any other portion of the control. Other things, we now have a voltage reduction button on the D. On the 2001Cs and prior, if you wanted to do local voltage reduction, you had to order the adapter panel with a toggle switch. Contacts of that switch would be wired hardware into 2 voltage reduction inputs. With the D, that is no longer necessary. We have a push button. We also have an LED like we did on the C. One difference in the LED is on the C, it was on solid if you were in any level of voltage reduction, and it was off if you were not in reduction. With the D, it will actually blink to tell you what level of reduction. So if you're not in reduction, it'll be off like it was in the C. But if you're in any level, let's say level 2, it'll be on solid for a few seconds, then it'll blink twice, go back solid, blink twice. So you count the number of blinks, that will tell you which level of reduction you are actually in. Now, to access the voltage reduction from the front panel push button, you must be on the home screen of the control. So if you're not on the home screen, if you keep hitting the exit button, it will ultimately return you to the home screen, and then if you hit the voltage reduction button, you should be prompted with which of the levels you'd like to enter reduction into. Another feature we've added is an alarm LED, and this alarm LED is programmable via the software. So when we bring up the Tap Talk, we can select any of these functions, and if any of them are selected and they are in the alarm state, the alarm LED will be on solid, and the home screen, instead of scrolling just the home text, will alternate between the home text and which alarm is active. If there are multiple alarms active, it'll scroll them one at a time. Once the alarm goes away, that alarm will no longer show on the screen, and if all the alarms are cleared, then the alarm light will go off automatically. So for instance, if we were on 16 raise and being blocked on tap position for a raise, the alarm light would be on and it would scroll block raise tap position. And once we got off of 16 raise, let's say we did a lower and came down to 15 raise, then that alarm light would automatically go off and the problem would have been fixed. With the H, we've also added an SD card. So we have a card slot on the front of the control. It uses a standard SD card. And if the card is plugged into the control, when you hit the communications button from the main menu, if it reads the card, i.e. it's properly formatted, then it'll come up with the memory card menu. Hitting the down arrow will allow you to select any of these quantities. So we can load settings from the control to the card. We can save them from the card to the control. We can save our data logging, our sequence of events we're going to be talking about a little later. Oscillography we'll be talking about. The clone, save, and load are similar to the set points, only they save or load everything, including all the communication settings. We also can save or load our DNP map, which on the D is a separate file. So in the C and before, the DNP map was part of the actual setting file. Now with the D, we have two separate files, one for the control settings and one for the DNP. Finally, we can update firmware from the SD card. When you do that, it's an automated function where it'll automatically place the control at manual. It'll copy the settings from the control onto the card, download the firmware, error check the firmware, download the settings from the card back into the control, and verify those with a E-squared checksum. And then if everything is normal, it'll automatically return the control back into automatic operation. And this process will take under a minute. So with updating the firmware on a C or prior, you needed a separate program. You had to go via the serial port, and it would take anywhere from 15 minutes to 30 minutes. Now with the D, we can do it via the SD card, not requiring a hardware laptop, and doing it under a minute. We also have a feature where you can download the firmware via Ethernet remotely. So if you have an Ethernet connection to the control, you can remotely download the firmware and not even have to go on site. So another feature of the SD card is it allows you to enter in one password onto the card, and then the control can have up to 30 unique passwords that it understands. Once you've configured this, when you plug your card into a control, it will automatically read the password, and if it's one of the 30 passwords it understands, it will automatically log you in and then log you out. And this is showing you the audit log. So we have a full NERC audit log that's logging when the users are entering and leaving the control. Over here is where we would place our SD card in our laptop. We would write our unique password down here and then write it, and then that's how we would get the password onto the SD card. So our HMI in the C used to be one long table basically. So the advantage of that was if you didn't know where a piece of data was, if you kept hitting the up or down button, sooner or later you would get to it. The disadvantage of that is if you knew where it was, you can hit a lot more buttons than needed, and it could take longer to get to that point. So with the D, we have now broken it into menus. And each of these up menus at the top have hot links off of the push buttons on the front of the control. So MON is monitoring, SETP is set point, CON is config, COMM is communications, and then our last one is utilities. Once you hit a button, then if you look at the bottom part of the screen, if you hit the left or right arrow, it'll tell you the next topic you'd be going into. But once you get to a topic that you like, if you hit the down arrow button, then it will drill you down. Or you hit the enter key, it'll drill you down. So all of these are sub-menus under the top menu of monitoring. Once we get to one of those menus, we can then go across using the arrow keys, or we can go down by hitting the enter. Once you're down, to go back up, you hit the exit button, and that will bring you up one screen. So if I were on resettable counters and I hit the exit button one time, it would bring me back to tap position. Hit it a second time, it would bring me up to monitor. Hit it a third time, and it would take me back to the home screen. So that's the basics on the navigation of the HMI. We also now are going to get into communications, and we have some physical differences in our communications. So here is a COM port fully loaded for a C versus a D. We do notice on the C we had a serial port that could either be fiber, 232, or 485. Likewise, we can have the same options on the D. We show an Ethernet port on the C, but it actually is not a full Ethernet implementation, but it is a terminal server. So it's actually a serial to Ethernet converter, which means that ultimate bandwidth is still 9600. You're still limited to one session and one protocol at a time because you're still interfacing ultimately with a serial port. On the D, this is a true 10100 Ethernet port. We also have the option on the D that was not there on the C for fiber. We'll talk about it a little bit later. So this is a true Ethernet port, unlike the C. And here's the fiber option. The copper option is 10100 auto negotiate. The fiber supports 100 FL with either ST or SC connections. So with our new Ethernet, we now support up to 8 simultaneous sessions at once, which means 8 different masters or users can be interrogating the control at the same time via the same Ethernet connection. Up to 5 of those can be DNP, and the remaining ones would have to be Modbus. We also support 61850 on the 2001D. For DNP, we support Modbus over both UDP and TCP. So, the 2001C did not support UDP at all. And we can remotely download firmware over the D, as we described earlier, if you have the Ethernet. That feature is not available on the C. So this is a typical block diagram of how a communications network may look with concurrent sessions. Here we have a D in the substation, and it may be being pulled by an RTU via 61850. We may have remote users wanting to get into it via Modbus to download settings or to look at oscillography or sequence of events. We may have a separate SCADA master with an IVVC application pulling the same control via DNP3. So the gist of this slide is that the 2001D can communicate with up to 8 different clients or hosts at the same time, of which no more than 5 can be DNP. We also have an option for a second serial port on the 2001D, and that serial port has two different options, the first of which can be a Bluetooth wireless. This feature allows you to communicate wirelessly within a few hundred feet of the control without needing to cable physically. So this is an advantage if you're out in the sunlight, or if you've got rain, if you've got snow, inclement weather. If it's a line regulator and the regulator controls are hung 20 feet up, and normally you would need a bucket truck to access them, these are all areas where the Bluetooth can provide benefit. The Bluetooth can communicate via either Modbus or via DNP. It is encrypted, and so it does have security and pairing, and you can hide the pairing. So it's a very secure wireless communications. Our configuration for the DNP is improved on the D. So on the C, we had each of the point types, and you clicked off what points you wanted, and the order they were clicked is the order they came back in. The disadvantage with that is if you originally did not click this point, and now you wanted it, every point below that would be moved down 1 point, and you would have to remap. We also did not support master address validation in the C. Master address validation says that when you receive a command from the master, don't just verify it's to your address, but also verify that it's from the master that you're being told that you're going to communicate with. We also did not support unsolicited on the C. So in DNP, there are three methods of communication. You can be polled continuously for data. You can do a report by exception, where normally you're only polled at very infrequent rates, and you only send back data that has changed since the last time it was polled. Or the third method is unsolicited, which is the master never polls the control. When the control has a piece of data that has violated a predefined limit, the control automatically sends that information back to the SCADA master. The C did not support unsolicited. The D does both unsolicited on serial and on UDP and TCP via DNP. The analog deadbands were fixed in the C. They're now user programmable, which is very critical when you start looking at centralized IVDC systems. Everyone needs a different resolution for when voltage changes, or when bars change, or when the tap position changes. And in the C, you were not allowed to configure. For instance, tap position deadband was set at 10, which means that the tap position would have to change by at least 10 taps before an exception was generated. With the D, you can set that to anything you want on a per point basis. And finally, we're going to talk about global addressing. But here's how we configure in the D now. We start by loading a template, which is on this side of the screen, and it basically shows us every point available for each of the different point types. We then simply drag and drop over what points we want. For instance, here in the analogs, and you can see we can also configure on a per point basis the deadbands, and also which class of data it's going to respond to if you're using a class 1, 2, 3 pole. When we're done, we also have the ability to do a print preview and a print, which is very nice for hardware documentation. As you can see up here, this is where we would enable the unsoliciting if we were to use it. And right here is where we would put in the master address if we were going to do source master address validation. So much more flexibility in the DNP mapping. Finally, we have a global scheme that we've added to the 2001D. And this is for serial DNP communications. Typically, DNP does support a global address, where if you receive a direct to operate with no acknowledgement, either analog or digital output, you would act on that control. The problem is other devices and other vendors also would support that global. So we were requested to come up with our own subglobals. So what we allow you to do on the D is define up to 3 different addresses for DNP serial communications. The end device address, which is the device everybody's used to, but then we allow you to enter in a feeder address and a station address. If a command is sent to the feeder or the station address, a control will only operate on it if it is a direct operate with no acknowledgement, either digital output or analog output. So therefore, in the case of voltage reduction, if I were to send a voltage reduction command to only this address, only this individual control would go into reduction. If I were to send it to the feeder address of 4000, these three controls would all simultaneously act on that command. And if I were to set it to the station address of 5000, then every one of these controls in this particular substation would act on the command. If you had every single substation set to the same substation address, then sending a command to the substation address would cause your entire system to operate at the same time. So if I wanted my entire system to go into voltage reduction at the same time with one command sent to the station address, if every station had the same station address, I would be able to accomplish that very quickly over serial communications. We also have added VPN as an option for our serial fiber on COM1. So the C had ST only. The D now also allows you for ST and VPN connections. One last thing is the second COM port on the D, besides being Bluetooth, can also be ordered with an RS-232 option. Now, if we get into the power quality, the first issue here we're going to talk about is data logging. The C had data logging, but it was for much shorter durations. And when you set a duration, let's say 5 minutes, you only had one value for that 5-minute period of time. So for instance, if you were data logging voltage, you would only have one sample during that 5-minute period of time. With the 2001D, we allow you to have both we give you 3 points instead of 1. So for a 5-minute duration, you're now going to get the minimum value during that 5 minutes, the maximum value during that 5 minutes, and the average value during that 5 minutes. Now that's not for every point, but it's for many of these points. Another difference between the data logging in the C and the D. In the C, if you did not have a point checked off the data log, it would not be logging it at all. Therefore, if you needed that point, you would have to enable it and then wait for it to get logged. With the D, everything is being logged all the time, and when you check these off, you're only checking off what points you want to bring up, but they're always available in the control all the time. So those are some of the enhancements we've done with data logging. We have also added graphical representation for data logging via the tap plot. So opening up the tap plot, here is your local voltage or your load voltage. Then here's the minimum and the maximum. So this is showing a case where we have not just the load voltage, but now this would be the average load voltage for each duration, the minimum and the maximum. And this is showing you just further information from data logging, showing you things like tap position, power factor, watts, VARs, op counter. Our next enhancement for power quality is we have implemented what we call a Sabima curve, but basically we allow a utility to define their definition of sags and swells, and then we can record those sags or swells. So what we allow you to do is to first of all specify your nominal voltage. Then we allow up to 4 different events. Each event can either be a sag or a swell. If you enter in a percentage above 100, it will be a swell. If it's below 100, it'll be a sag. So you can enter in when we pick up what voltage has to be to drop it back out or return it to normal, and then the minimum duration of time before we trigger. So in this case, if the voltage gets below 70% of 120 for more than one cycle, we will trigger, and we will stay triggered until the voltage comes back up to 95% of 120. Down here in this bottom example, the voltage would have to exceed 120 by 110% for more than one cycle, and then it would have to return to 120 before we considered it back to normal. Once we trigger, we can then either just have these events go into sequence of events, so we time stamp to know the duration, or we can just accumulate a counter that goes back to SCADA that tells us how many of each operation we've had. We also have an alarm to DNP that tells us the duration in cycles of the most recent event, or we can actually capture some waveform for the event and view it. And this is what it would look like in viewing the waveform. So this is oscillography coming back from the TapPlot program, which is a free extension of the new TapTalk. And you can see that we've had a sag on the voltage, and it looks like a fault as we've got the current also being altered. And there's our Sabima pickup. So this is what a typical fault record for a sag would look like. Now, the C did harmonics, but it really did not. It allowed you to do odd only, and it would actually read several values from the control to TapTalk, and TapTalk would actually calculate the harmonics. In the D, it is actually sampling 64 samples per cycle, which allows us to record within the control itself both even and odd harmonics up to the 31st harmonic. We can then either look at the harmonics real time and see their percentages, or we can set them to trigger either sequence of events or oscillographies, and also have alarming back to DNP when we have harmonic violations. The 2001D also comes with a sequence of event recorder. It does not currently support IRIG-B, but does allow for time setting via DNP set time command to synchronize the clock. We have 129 events, and each event can be programmed. So we would click on what we want to trigger events both for pickup and dropout, and anything that is checked off will be an event, and therefore will go into the event log, and we will have the most recent 129 events. And then we have a portion of the TapTalk allows us to view each event. So each of these is a different event, time stamped with when the event was. Down below we see the different things that were active during the event. We can also look at some of the metering quantities that were present at the time of trigger, and also look at what the harmonics we're looking at the time of trigger. Oscillography. We can trigger up to 16 different records, and each record can be set to either use 16 samples per cycle, 32 samples per cycle, or 64 samples per cycle. Obviously, the higher the sample rate, the shorter duration each record's going to be, and the more records you have, the shorter duration each record will be. Within each record, you can have a certain percentage be recorded pre-trigger and a certain percentage post-trigger. So in this case, this is where we would select how many different records we want, what we want the sample rate to be for each record, what percentage of each record is going to be pre-trigger versus post, and then what different things we want to trigger an oscillography. And again, this is what an oscillography would look like. We also allow you to monitor the motor current, unlike the C. So for single phase regulators, we can actually monitor the motor current, and that is triggered. So as it is tapping, we can not only see the load voltage and the load current, but we can also see the motor current. And we can see as the motor turns on, it draws exponential current, then it settles in, runs the tap, then turns off. In this particular record, we can also see a lot of harmonics on the current. So with our motor current, we can look at three different things for maintenance. We can look at the peak amount of current, the average current, and the average duration the current is present. So when you first power up a 2001D, it will enter training mode. In training mode, it is going to record the average of the first 20 operations, either raise or lower, manual or automatic, it doesn't matter. But we will average the first 20 operations, and once we have that average, that will be the default. Then you can set percentages above that, and if those percentages get exceeded, we can generate alarms back to SCADA. So for instance, if the average tap is 4.6 seconds, once the regulator starts requiring 6 seconds to make a tap, it's slowing down, and we can generate an alarm to SCADA to allow us to know that, so that we can do maintenance. And this is where we would set those percentages in the new version of TapTalk for the 2001D. We also now have 4, and we will shortly be going to 8 profiles. So the 2001C only had one setting profile. The D has multiple profiles, and within each profiles you can set different band centers, different bandwidths, time delays, RX, and there are multiple ways to go from one profile to another. You can have SCADA send a command to go from one profile to another. You can have a contact input on the control drive it from one profile to another. You can have reverse power drive it from one to the other. Or you can have time change it from one profile to another. And this is what the settings would look like. So for each profile, everything you see on this screen can be set differently for each of the currently 4 profiles and ultimately up to 8 profiles. We've also added a second physical PT input on the 2001D. The 2001C had only one PT input. That made it very difficult to use with line regulators, where if you had 2 PTs you can actually measure the voltage on both sides. But if you only have one, you have to use the tap position to calculate the voltage on the other side when you're in reverse power. So in the D, we have added a second PT input, and therefore we have added ratios on the screen for the second PT. So you have your primary, your regular PT up here, but then we also have a second PT input down below. And that second PT input physically comes into a new connector. You can see on the 2001C we have our main blue connector, which is the same on both. We have the shorter connector, which was used for either bringing in tap position or bringing in external power, and that is the same on the D. But notice we've added a new connector on the D, and one of the pins on that connector is where we would physically bring in that second PT if it were available for line regulator applications. With that, we now have a new reverse power option. So in the C, you've had regulate in reverse, which says in reverse power, our regulator source side is now the load side, and the load side is now the source side. So my PT is on the wrong side of the regulator, and I will need to calculate what the voltage is on the load side by using the source side PT I'm now monitoring and the tap position. Regulating in reverse measured says that we now have the second PT in the control. The PT is on the regulator, and in forward mode we will use the load side PT to measure for the load side, but in reverse power mode we will switch over to the source side PT, which now becomes the load side. So if you have the 2 PTs available, you would select regulate and reverse measured, and the control would toggle between which of the 2 PTs it was looking at. If you still only have one physical PT, then you would still, as you did in the C, select regulate and reverse. We've also added a new feature to help coordinate the regulator or LTC with downline capacitor banks. Many utilities, as part of their IVBC system, want to have capacitors start acting more as voltage regulation as opposed to just VAR or power factor correction. Some of the advantages are that we can reduce the number of operations on our LTC or regulator and allow the capacitor banks to regulate the voltage. And we can also flatten out the profile so that we can have enhanced voltage reduction capabilities. So we can only reduce the voltage at the source as much as the end line voltage allows us to. So if we can have the end of line voltage be closer to the source voltage, then we can get additional voltage reduction, and capacitor banks allow us to do that. So the way the VAR bias works is you enter in the largest switch capacitor bank you have downstream to this control, what percentage you want it to operate lead and lag. So if I enter 75 and 75 for a 1200 kVAR cap bank, what the control says is if I go more than 900 kVAR lagging, I don't want to raise the voltage. I'd rather have the capacitor bank closed to raise the voltage. Likewise, if I'm more than 900 kVAR leading, I need a cap bank to open as opposed to the LTC or regulator lowering the voltage. So the way VAR bias works is if the VARs are outside these bands, we will actually bias one of the two band centers by this voltage to encourage the LTC not to tap in that direction. And we will hold that bias for a predetermined amount of time just in case the capacitor banks are not in service. So if I have lagging VARs and the voltage needs to be raised, I would rather the capacitor bank close. So I'm going to bias my voltage in one direction by upwards of 2 volts, so I will not be encouraged to raise the voltage. But after a fixed amount of time, if the capacitor bank has not closed and my VARs have not come back in to range, then I will take the tap and I will actually generate an alarm to SCADA. And when SCADA sees that VAR duration alarm, it knows that either I do not have enough capacitance on the circuit and I need to add another switch capacitor bank, or one of my existing banks is out of service and I need to go out and maintain it. Another feature we've added for regulators is what we call run through neutral. And this is mainly to exercise the reversing switch. And the way this particular setting works is the user can determine how many taps the regulator has to go without going through neutral before you want the control to automatically run it through neutral. Once the control has exceeded that number of taps without going through neutral, it will enable this feature. But this feature still needs to see the regulator come within X number of taps of neutral. Obviously, if you're at minus 14, you probably don't want to raise the voltage 14 taps just to exercise the reversing switch. So this say you put in 4 taps. What that tells the control is when I get within 4 taps of neutral, either 4 raised, 4 lower, I will automatically temporarily go into manual and I'm going to drive it 1 tap past to actually exercise the reversing switch. So for instance, if I were at 4 lower and I were set to 4 taps, I would actually go into manual temporarily. I would drive it up to 1 raise and then put it back into auto and let it auto-regulate back again. So remember, when you're putting in the number of taps, you have to add 1 to that because it's not just getting to neutral, but going 1 tap past neutral. This bottom one is once the feature is enabled, it may not be able to run to neutral immediately because either the number of taps may not be within the limit or the load current may be outside the limit. So once you go this number of taps without it being able to run through neutral, it can generate a secondary alarm saying, I've been wanting to run through neutral, but the conditions have not been satisfied to allow me to do that. Another feature we've added mainly for regulator but also LTC scenarios is something called remote voltage bias. And this is mainly due to distributed generation on a distribution circuit. If you're using line drop compensation, the control will place a line drop R and X value off of the load current it sees. So as an example, if I had a band center of 120 and an R of 4, at full load, I would add 4 volts to the 120 and I would have a new band center of 124, expecting a 4 volt drop across the circuit. The problem with DG is I still have a lot of load going through that circuit, but if some of that load is being provided by DG downstream of the regulator CTs do not see that full load and therefore they are not applying the proper amount of compensation. So in the previous example, if half the load was being served by DG, now the regulator, instead of seeing the full load and applying 4 volts, is only going to see half the load and will only be applying 2 volts. This can lead to the customers at the end of the line having low voltages. To help stop that, we have a new feature that can be enabled called remote voltage bias. Basically, what the remote voltage bias does is it allows SCADA to pull an end device such as a capacitor control, revenue meter, or monitoring point and actually get the end line voltage and then send that to the control. The control then, instead of using line drop to try to determine what the voltage is at the end of the line, will actually use the end of line voltage. So if the end of line voltage is 118 and my band center is set at 120, I know there's a 2-volt drop, so I would raise my band center to 122, which would then in turn theoretically get the end voltage back up to 120. Now, if communications is lost to the end sensor or the SCADA, then we need to come out of remote voltage bias mode and go back to using traditional RX, and that's what this heartbeat timer does. So in this case, in 5 seconds, if I don't get a new update every 5 seconds on the inline voltage, then I will disable the remote voltage bias and go back to RX. So if you have RX settings and remote voltage bias enabled, it will use the remote voltage bias to determine the line drop as long as the heartbeat is present. If the heartbeat is gone, then it'll switch back and use your RX settings instead. Another feature we've added for regulators is something called low current block. Low current block is used in the scenario where you may have single phase regulators inside the substation on each feeder. And the scenario is you have one of the feeders out of service and that circuit is tied to another substation. So now that set of regulators, instead of being at the front of the circuit in forward mode, are actually at the very end of the circuit in reverse power mode. The problem is there's no load current on those regulators, so there's not enough load for it to determine that it is in reverse power mode. So what may happen is if that little piece of bus voltage gets out of band, the regulator will attempt to fix it, and since it is on the wrong side of the regulator, it will not see that correction happen, and you could have a runaway condition, which doesn't hurt the voltage currently because there's no load on it. But when you go to switch everything back and you close that circuit breaker back in, your regulator now could be many taps off of where it was, and therefore the way the low current block works is if the current is below 4 milliamps in either direction and the regulator taps, the control will look at the new voltage. If it goes 2 consecutive taps without seeing a voltage change, it assumes it is now on the wrong side of the regulator and that we are actually in reverse power, and it will block and stay blocked until the load current comes back above 4 milliamps. And we would enable that feature right here on the version of TalkTalk. A final feature that we've added for transformer LTC applications and for paralleling is we have one method, and we'll be adding a second method in the next release for paralleling using communications. So the first method is a master-follower scheme in which you would identify one of the controls as a master, the others would be followers, and the master and all the followers will be hooked up on the same Ethernet network. So they'll all be cabled into the same switch. They'll be using 61850 and goose messaging, and the master will goose out its tap position, and the followers will subscribe to that tap position, and their goal is to stay on the same tap. They will also subscribe out their tap positions, and the master can subscribe to them to verify that they are staying in the same tap, and if not, within X number of programmable taps, you can have the system locked out. We also have to look at the line breakers to determine whether we're in parallel or not. So now in paralleling, we've always had in the C the circulating current, the delta var 1 and 2, but now we've got some new ones, and we're going to talk about this master follower. So when we select master follower, I can select each control for either master or follower. This setting is only used on power up, and it defines which one is going to be the master on startup. So we would only want one to be master, the others would be followers. Now, when a master goes down, the followers will determine that, and one of the followers will be elected the new master, and that is done off of the actual address. So the address, the control with the highest address should be deemed the master, and then if that one fails, the follower with the next highest address will automatically become the master. We also then say how many total devices are going to be in parallel. What is the allowable tap difference between the master and any one of the followers before we lock out? And then what amount of time is allowable after a master tap before it expects the followers to also tap? Obviously, different mechanisms have different times, so we need to allow for that. We're also going to look at the line breakers, breaker to the right, breaker to the left, and the low side bank breaker. And positive polarity means it's a 52A contact, negative polarity means it's a 52B. And if you don't have a contact for that particular breaker, you would put not in use. Now, these breaker contacts need to be brought into new physical controls on the D. So those are what the other pins on that green connector are being used for, is to be used to bring in the 3 breaker contacts. And these contacts will be wetted off the 24 volt supply of the control.